Welcome to the Data Genius podcast.
Glad to be here for this one.
So we have an incredible deep dive for you today. We're unpacking the massive revolution in AI reasoning models from 2025 and 2026.
It really was a huge shift, going from models that just talk to models that actually think.
Exactly. And our mission today is to synthesize a giant stack of sources for you. We've got industry reports from Xylos Research and Tascade, plus some intense academic papers.
Right, papers on things like tree of thoughts, React, and Monte Carlo tree search, which sound complicated, but we'll break them down.
We definitely will, because by the end of this deep dive, you'll understand exactly what test time compute is. You'll learn why AI learned to hesitate before speaking, and how you can actually apply this to save time and reduce cloud costs.
And build reliable autonomous agents, which is the holy grail right now.
Without drowning in technical jargon, I promise. So to kick this off, let's talk about the 2024 AIME math competition.
Oh, the AIME benchmark. That's the perfect place to start.
Right, so you have this incredibly brutal high school math test, and GPT-4o takes it, and it scores like 12%.
Yeah, just a complete and total failure.
But then a few months later, OpenAI's O1 model takes the exact same test, and it scores around 74%.
A massive leap. And the crazy part is, the training data didn't even drastically change between those tests.
Exactly. It's not like it suddenly read a million new math books, so why did it suddenly get so much smarter?
Well, it fundamentally comes down to that hesitation you mentioned earlier. We're so used to computers acting instantly, right? You hit enter, you get an answer.
Yeah, I mean, if a search engine takes more than a second, I assume my Wi-Fi is down.
Exactly. Traditional large language models, or LLMs, were built on that instant reflex. They operated in what psychologists call System 1 thinking.
System 1 being like fast and intuitive.
Right. Traditional LLMs are just predicting the very next token or word in a sequence. You give it a prompt and it instantly starts blurting out the answer in a single forward pass.
Like if I ask you the capital of France, you just say Paris. You don't have to diagram the map of Europe in your head.
Yes, but if I ask you a complex logic riddle and you just blurt out the first word that comes to your mind, you're probably going to get it wrong.
Oh, for sure. I'd need a notepad.
And that's exactly what the traditional LLMs lacked. They hit a wall in advanced coding and math because they couldn't pause to work through intermediate steps.
So the O1 model that scored the 74%, it just took its time.
Conceptually, yes.
Yeah.
But mechanically, engineers unlocked a totally new scaling law. Before this, we basically had two ways to make AI smarter.
Right, which were pre-training and post-training.
Exactly. Pre-training scaling is just the brute force method. Build a bigger neural network, shove more internet data into it.
And post-training is fine-tuning it with human feedback so it doesn't sound like a robot.
You got it. But the new era introduced the third law, which is test time compute scaling.
Test time compute. Let's break that down for everyone. Test time just means the moment you actually ask the AI a question, right?
Right, the moment of inference.
So we are spending more compute, more processing power after you ask the question, but before it gives you the answer.
That is the core mechanism. The model gets a computational budget to generate what we call hidden thinking tokens.
Hidden tokens, so it's talking to itself.
Basically, yeah. It pulls out a digital scratch pad. It works out the math, maybe realizes it made a mistake, crosses it out, and tries a new formula.
And we don't see any of this.
Usually, no. Only when it has a verified conclusion does it generate the final output for you. That is System 2 thinking. Slow, deliberate, and analytical.
Okay, wait. If it's still fundamentally an LLM, meaning it's just predicting the next word based on probability, how is this actually thinking?
That's a great question.
Like, isn't it still just an autocomplete engine doing its thing behind a curtain?
It is predicting tokens, but the context window changes everything here. In a normal model, if it makes a tiny error on the third word, every word after that is built on a flawed foundation.
Right. It hallucinates and goes totally off the rails.
Exactly. But when it generates a reasoning trace on a scratch pad, those hidden tokens become context for the next token.
Oh, I see.
It lays out a logical premise,
Yeah.
evaluates it, and uses that premise to guide the next prediction.
So it's like writing a map for itself before it starts driving the car?
Precisely. And there's a fascinating paper in our sources by Snell and colleagues about this. They proved that a much smaller model can actually beat a massive model if you optimize its test time compute.
Wait, really? A tiny model can beat a giant one?
Yes. A smaller model with a budget to generate thinking tokens can outperform a traditional model that is up to 14 times larger.
That completely changes the economics of AI. You don't need a trillion parameter monster if a smaller model can just sit and ponder for 20
A
seconds.
huge paradigm shift.
But let me push back on that. Is there a limit? If thinking longer makes it smarter, what if I let it think for a week? Will it cure a disease?
Well, no. And that's a crucial nuance about test time compute.
So thinking for an hour doesn't guarantee a better answer than thinking for a minute.
Definitely not. The scaling curve has distinct diminishing returns. Going from zero thinking to some thinking makes accuracy shoot straight up,
Right, huge leaps in logic.
but eventually the curve flattens. And in some domains, accuracy actually dips if it thinks too long.
Why would it dip? If I spend an hour on a riddle, I'm usually closer to the answer.
Because an LLM can get totally lost in the weeds of its own context window. If you force it to think for an hour on a basic coding problem, it exhausts the logical path.
So it starts overthinking.
Exactly. It starts exploring highly unlikely edge cases and bizarre what-if scenarios. It dilutes your original prompt and second-guesses its own correct logic.
Wow, so finding that exact right thinking budget is the real challenge.
Arguably the biggest engineering challenge in the industry today.
So we've got this massive shift from blurting to thinking. Let's look at the titans actually building these models, because how they handle this hidden scratch pad is creating a massive rift.
A huge rift.
Yeah.
It's basically a war between proprietary, closed-source ecosystems and radical open-source transparency.
Right. So OpenAI really started this with the O series. We had O1, and moving into the 2025 and 2026 data, we've got the O3 and O mini models.
And their benchmarks are just terrifyingly high.
Yeah, the sources highlight the ARC-AGI benchmark. Traditional models scored practically zero on this, right?
Yeah, because it's not a text test. It's abstract visual reasoning.
Right.
You have to deduce logic from colored grids.
And O3 scored over 45% on that, plus it got 100% on the competitive programming benchmark.
But OpenAI's architectural choice is absolute opacity. They hide all those reasoning tokens.
Total black box. You submit a prompt, it says it's thinking for 30 seconds, but you have no idea what it's actually doing.
You only see the polished final answer. You don't know if it did brilliant calculus or just got lucky down a rabbit hole.
Which contrasts wildly with DeepSeek. The sources treat DeepSeek R1 like an earthquake in the industry.
It really was, because they proved you don't need massive amounts of human data to build a reasoning model.
Right, they used pure reinforcement learning. The algorithm is called GRPO, I think.
Yes, GRPO.
Okay, so group relative policy optimization. What does that actually mean for, normal people?
Think about training a dog. The old way, supervised fine-tuning, is like physically taking the dog's paw, placing it in your hand, and saying shake.
You're demonstrating the exact steps for the AI.
Right. But GRPO is like holding a treat, looking at the dog, and just waiting.
Just staring at it.
Yeah. If it barks, nothing. If it spins, nothing. But if it randomly lifts its paw, boom, you give it a treat.
So DeepSeek just gave the AI math problems and set up a reward system.
Exactly. No human examples. Just a digital reward if the final answer was mathematically correct and formatted right.
So at first, the AI is just throwing spaghetti at the wall.
Yes, but GRPO optimizes it by having the model generate multiple different responses to the same prompt. That's the group part.
And it scores them against each other?
Right. The model learns which sequences of hidden tokens lead to the highest reward, and the emergent behavior was stunning.
It just spontaneously developed a chain of thought.
All on its own. It taught itself to pause, try different strategies, and check its work, just to get the mathematical reward.
That is incredible. And DeepSeek's defining feature is that it's totally transparent. You literally get these little tags that say think.
Yes, the think tags. You can read every single word of its internal monologue.
Which has to be a revelation for developers. I mean, if the math is wrong, you just read the tags and find the exact broken step.
It makes debugging so much easier. You can actually verify the logic.
So if transparency is that good, why would OpenAI hide the engine entirely? Like, isn't DeepSeek objectively better for developers?
Well, it comes down to safety, economics, and architectural freedom.
Safety. How does hiding the scratch pad make it safer?
Think about a user asking how to synthesize a dangerous chemical. The AI's final output might safely say, I can't help with that.
Right.
But to figure out it shouldn't help, its internal reasoning trace might have actually mapped out the chemical synthesis.
Oh, wow. So the final answer is safe, but the scratch pad is essentially illegal material.
Exactly. Broadcasting the internal thoughts bypasses safety filters, plus there's the economic side.
Right, the architectural freedom you mentioned.
If OpenAI exposes the reasoning tokens, developers will build apps that rely on that specific formatting.
Oh, I see. Then OpenAI can never change how the AI thinks without breaking thousands of external apps.
Precisely. By hiding it, they can overhaul the reasoning engine overnight, and the developer only ever interacts with the final input and output.
Makes total sense. The classic Apple closed ecosystem versus the Linux open source vibe. But we also have Google and Anthropic jumping in.
Yes, and they take very different approaches to this thinking budget. Google's Gemini 2.5 uses dynamic thinking.
Because waiting 30 seconds for every query is a terrible user experience, right?
It's awful. So Gemini automatically scales its effort based on how complex your prompt is.
So I asked for a pancake recipe. It just uses a fast, cheap pathway.
Right. But if you paste in a huge block of broken Python code, the model detects the complexity and automatically allocates more test time compute.
It's trying to read your mind on how hard the problem is. Now, Anthropic went the other way with Claude 3.7.
Yes, they gave the power directly to the developer with budget tokens.
I love this concept. You basically tell the API exactly how much to think.
You set a floor and a ceiling. You can say, you must spend at least 1,024 tokens thinking, but do not exceed 10,000.
It gives developers total control over latency and cost. But let's talk about the most disruptive thing coming out of the open source side, which the sources highlight constantly: distillation.
Distillation is fascinating. It fundamentally changes who gets to use these models.
Right. It's essentially knowledge transfer. Explain how DeepSeek pulled this off.
So they have their massive R1 model, 671 billion parameters. It costs millions in GPU hardware just to run.
A total beast of a model.
They fed it complex problems and recorded its high-quality reasoning traces, about 800,000 of these deep reasoning samples.
So they recorded the master at work.
Exactly. Then they took a tiny 8 billion parameter model, one you could run on a good laptop.
And they trained the tiny model on the big model's scratchpad.
Yes, not on raw internet data, but strictly on the reasoning traces. The small model learned the patterns of reflection and self-correction.
So the giant model acted as a private tutor for the small one.
And it shattered what we knew about AI scaling. That tiny distilled model hit reasoning benchmarks that used to require supercomputers.
It proves you don't need a massive model for complex logic. You just need a small model that's been taught how to think.
It totally democratizes advanced reasoning.
Okay, but when we say the AI is thinking, people picture a human brain pondering. But it's just software. It's executing algorithms.
Right, it's all math under the hood.
So how does a token predictor actually navigate a problem without just guessing? Let's get into the specific algorithms of the internal monologue.
The foundational framework here is the tree of thoughts, or totite.
Because before this, we just had chain of thought, right? Where you type think step by step.
Yeah, but that was strictly linear. Step 1, step 2, step 3. If step 1 had a flaw, the whole chain collapsed. It couldn't backtrack.
Like walking a tightrope. One slip and you're done. So tree of thoughts changes the geometry.
Exactly. It treats reasoning as a branching tree instead of the straight line.
My favorite analogy for this isn't a chess grandmaster, it's a detective with a string board.
Oh, that's a good one.
Right. You have the crime in the center. You don't just follow one suspect linearly until you hit a dead end. You branch out. If suspect A did it, timeline A happens. If suspect B, timeline B.
You explore multiple timelines simultaneously, and Toady handles this in 2 phases: generation and evaluation.
Okay, generation is making the branches.
Yes, producing candidate thoughts. And the model is smart enough to change its generation strategy based on the task.
How does it know which strategy to use?
Well, if it's a creative task, like writing a unique marketing strategy, it uses a sample strategy. It brainstorms wildly different branches for a broad search space.
Because you want diverse ideas.
Right. But if it's a rigid puzzle, like using 4 numbers to equal 24, random brainstorming is useless.
Yeah, you need strict math.
So it switches to a propose strategy. It proposes strict, sequential mathematical operations, expanding the tree one logical step at a time.
Okay, so our detective has generated 5 different timelines on the string board. How does the software evaluate which string to follow?
This is where evaluation algorithms come in. Because you're right, if it hallucinates a bad idea, it needs to catch it.
Otherwise, it confidently walks right off a cliff.
Exactly. So 2T uses 2 primary evaluation strategies. The first is the votes strategy.
The model votes on its own thoughts.
Yeah, it looks at all 5 branches in its context window and acts as an internal jury voting on which branch seems most promising.
Comparing them side by side, what's the second strategy?
The value strategy.
Yeah.
It acts as an internal critic and assigns a concrete mathematical score to a specific state.
Like grading it on a scale of 1 to 10.
Essentially, it asks, How close is this current state to the final solution? Once everything has a value, it uses classic search techniques, like breadth-first search.
Okay, breadth first search. So it explores all initial branches, drops the low scores, and only expands the best ones.
And if it hits a dead end where all values drop to zero, it actively backtracks up the tree and tries a different branch.
That makes perfect sense for a static puzzle, like math. But what about the real world?
The dynamic environments are much harder.
Right. Our sources talk about AI agents navigating live websites, like booking a flight where pop-ups happen and buttons move. A static tree would just shatter.
Which brings us to the Plan MCTS framework, Monte Carlo tree search adapted for web navigation.
And the big innovation here is decoupling, right?
Yes, it aggressively separates plan exploration from action exploitation.
Let's translate that. What is plan exploration?
It happens entirely in the abstract space. The AI is reasoning about high-level intent, like, my goal is to find a red sedan under $8,000. My subplan is to find the search bar and filter by price.
So it's just building a roadmap. It isn't thinking about clicking pixels yet.
Exactly. Action exploitation is the physical grounding. That's the local operator translating the plan into physical execution.
Like, where exactly is the search bar in the HTML code? Which coordinates do I click?
Right.
But why separate them? Why can't the AI just think, click the search bar to find the car?
Because websites are messy. If intent and action are combined and a newsletter pop-up blocks the search bar, the action fails.
And if it fails, the AI just gives up on the whole plan.
In older models, yes. It would abandon the idea of searching for a car. But by decoupling them, Plan MCTS introduces a dual gating mechanism.
Dual gating, a two-step evaluation. Walk me through that.
First is micro-verification. The local operator asks, did the action I just took complete my immediate subplan?
So if it clicked the search bar but no text appeared, micro-verification fails.
Right. The AI realizes a pop-up is in the way. It closes the pop-up and retries the action. It doesn't abandon the grand plan.
It has localized persistence. I like that. And the macro assessment.
Once micro-verification passes, it asks, did this sequence of actions move me closer to the global goal?
So if it typed red sedan, but the website shows bicycles, the macro assessment fails.
Exactly. The AI realizes the website's search function is just broken. It needs a completely new high-level plan, maybe navigating to a different site.
Dual gating lets it recover from small execution errors without losing sight of the big picture.
It's a huge leap in autonomy.
But this reliance on self-evaluation brings up a huge vulnerability.
Well,
We're trusting the AI to be its own micro-verifier.
it is a risk, yes.
I mean, if I write an essay and proofread it myself, I'll miss my own typos. My brain wrote the words, so it expects it to be spelled right. I need a harsh teacher with a red pen.
That is one of the most critical debates in the field. And the machine learning mastery research we reviewed provides a clear empirical answer.
Which is?
Self-correction is real, but it is entirely dependent on an external source of truth.
So the harsh teacher is mathematically required.
Absolutely. If you just prompt an LLM to find its own logical errors, it falls victim to confirmation bias.
It uses the same flawed logic to reaffirm its mistake.
Or worse, it hallucinates an error that doesn't exist just to please your prompt. You need a grounded critic.
Give me a tangible example of a grounded critic.
Software engineering is the best example. If an autonomous agent writes a Python script, you don't ask the AI if the code is good.
You actually run it.
Right. You execute the code through a testing framework like PyTest. The external compiler is the grounded critic.
The code either passes or fails. It's objective.
And if it fails, the compiler generates a traceback error log. The agent can't hallucinate its way out of a syntax error.
It needs reality to punch it in the face before it realizes it made a mistake.
Exactly. It feeds that objective failure back into its context window, analyzes the error log, and successfully self-corrects.
Our sources point to a framework that structures this loop called self-refine. How does that optimize the feedback?
Self-refine dictates that feedback must adhere to two strict principles. It must be actionable, and it must be specific.
So an error message saying, this code is too slow, is useless.
Completely useless. Actionable means suggesting a concrete modification. Like, the nested loop is causing O(n)(2) time complexity. Consider a hash map.
Oh, that's way more helpful.
And specific means pointing directly to the exact offending line of code. The loop iterates through generation, receiving specific feedback from the critic, and refining the output.
And when you scale this up to an agent actively browsing the web or using databases, you enter the React framework, right?
Yes, reasoning and acting interleaved. The AI generates a thought, takes an action in the environment, observes the result, and generates a new thought.
But the true intelligence here is in the dynamic switching heuristics.
The rules of thumb it uses to know when to switch gears.
The sources highlight uncertainty-driven activation. How does an AI even know it's uncertain?
It measures consensus. Imagine it generates 5 parallel paths using tree of thoughts for a medical question. If all 5 converge on disease A, it has high confidence. But if 3 say disease A and 2 say disease B, consensus collapses.
But the model realizes it's confused.
It recognizes its own internal uncertainty. That mathematical threshold triggers the heuristic.
So what does it do?
It switches out of internal reasoning and activates the react loop. It decides, I don't have enough reliable info in my weights. I need to search the PubMed database.
It uses external action to resolve internal uncertainty. That is profound. It literally knows what it doesn't know.
It's a critical safety mechanism.
But what if it searches PubMed, doesn't find it, searches Google, fails again, writes a scraping script, and still fails?
The infinite loop problem.
Right. If the AI is locked in a loop, am I going to wake up to a $5,000 cloud bill because it spent 3 days trying to fix a broken Python script?
That's the danger, and it's why you need the static fallback heuristic. You have to engineer a circuit breaker.
So how many tries does it get?
Usually a maximum of 3 to 4 iterations. The agent attempts, fails, self-corrects, and tries again.
And if it fails, 4 times.
The system physically severs tool access. The agent is forced into static fallback, generates a summary of the failure, and hands the log to a human.
A reliable agent knows exactly when to stop burning compute and ask for help.
Exactly.
Which transitions perfectly into the concept of continuity. If an AI is operating over time, handing off logs, taking actions, it needs memory.
Managing the memory of a persistent agent is arguably the most complex architectural challenge right now.
Because we're moving from a single chat session to a persistent agent that works for you for months.
The naive approach was the conversation buffer. The system just copy-pasted your entire chat history into every new prompt.
Which is fine for 10 messages, but if it's organizing my life for a month, that history is millions of words long.
And that creates 2 massive problems: cost and pollution. We'll get to cost, but the pollution is fatal.
How so?
If you feed an AI 1,000,000 tokens of unfiltered interaction, every typo, every abandoned idea, the important facts get buried.
Attention dilution.
Right. It can't distinguish durable facts from transient noise.
It's the difference between short-term RAM and long-term storage in human memory.
That's a great way to put it.
Like, you remember a phone number just long enough to dial it, then you forget it. But you store your spouse's favorite food in long-term memory?
Exactly. You don't keep their favorite food actively in mind while doing your taxes, but you can retrieve it instantly for dinner.
And that analogy maps perfectly to the RAISE architecture from our sources. Memory-enhanced architecture.
Yes. RAISE divides AI memory into distinct functional components to solve that pollution problem.
Let's unpack them. We have the scratchpad, the example pool, and task memory. What's in the scratchpad?
The scratchpad is the short-term RAM. It only contains context for the specific action it's taking right now.
So if it's on a website, it holds the HTML layout and the immediate goal.
Right. And the moment the task is done, the scratchpad is wiped clean. It's strictly for the present moment.
And the example pool.
That's where vector retrieval comes in. When you give the agent a complex new task, it translates that task into a mathematical vector.
A coordinate in high-dimensional space.
It searches a long-term database for past successful scenarios with similar vectors and pulls them into the prompt.
Like saying, here's how you handled a similar situation 3 weeks ago.
It grounds the agent in proven strategies without overwhelming it with irrelevant history.
Retrieving operational wisdom. And finally, task memory.
Task memory records the agent's trajectory, the sequence of thoughts, actions, and corrections during a task.
But how is this managed? The sources mention the hot context lifecycle.
Yes, prehydrating a workspace. When an agent wakes up to do a job, it doesn't load its whole life history.
What does it do?
The system prehydrates a workspace. It selectively pulls specific user preferences and relevant context from the example pool into a temporary active state.
It only brings the tools it needs to the workbench.
Exactly. The agent operates exclusively within this hydrated hot context. And when the job is done, the most important step happens: curation.
Wait, let me push back here. We have models with context windows of 2 million tokens now. Why do all this complex retrieval and hydration?
I get that a lot.
Why not just shove every document and log into the context window every single time? The AI can handle it.
It can handle it computationally, but you cannot handle it economically.
Ah, right.
Every time you feed 2 million tokens into a reasoning model, you pay for the compute to process them.
The meter is always running.
If your agent makes 50 tool calls for a task, and you feed it 2 million tokens on every loop, you'll bankrupt your project in an afternoon.
That makes total sense. So the curation step is financially necessary.
Yes, and necessary to extract durable knowledge. The system usually uses a secondary, much smaller, cheaper LLM to act as a librarian.
A librarian.
It reads the messy transcript of the completed task. Its only job is to extract stable facts.
Like, the user changed their database preference to MongoDB.
Exactly. The librarian distills those facts and writes only those specific updates to the long-term vector database.
So the cheap librarian cleans up the expensive reasoning worker's desk at the end of the day. That is incredibly elegant.
It really is.
But you brought up cost, which brings us to production realities. We know these models are brilliant, but how do businesses actually afford them?
That is the central challenge of 2026. The proof of concept phase is over. We're in deployment, and the blockers are quality and latency.
Latency is a killer. If I open a customer service chat and ask about a refund policy and it spins for 45 seconds, I'm closing the tab.
The user is gone. You cannot use a deep reasoning model for everything. It's massive overkill.
So what's the solution?
The router architecture. It's become the absolute standard, as detailed in the Cascade reports.
Essentially, you don't hire a massive corporate law firm to fight a $20 parking ticket.
Great analogy.
You handle the ticket yourself and hire the law firm when you're merging two companies. You route the task to the appropriate intelligence.
Exactly. A router is a fast, cheap, lightweight classifier model sitting at the front door.
It doesn't answer the query, it just assesses the complexity.
Right. If you ask, what's the refund policy? The router sends it to a fast LLM. The response takes milliseconds and costs fractions of a cent.
But if I paste in 1,000 lines of code and say, debug this failing test and rewrite the authentication logic.
The router recognizes the high complexity. It bypasses the cheap models and sends it directly to a deep reasoning model, like an O3 or Claude 3.7.
And you gladly accept the 30-second latency because a wrong answer there would be catastrophic.
Exactly. And there's a fascinating economic shift here. Traditional LLMs scaled cost with output length.
A 10-page essay cost more than a single sentence.
Yes, but with reasoning models, cost scales with problem complexity.
Because you're paying for the hidden reasoning tokens. The longer the scratch pad, the higher the bill.
If you point a reasoning model at a simple task, you're literally paying it to overthink.
That's why routing and budget caps are so critical. And the ultimate goal moving forward is efficiency scaling, right?
Yes. Taking the capabilities that cost $1 million in compute for an O3 and figuring out how to solve them for $1.
The industrialization of thought, making System 2 reasoning practical for everyday software.
It's changing everything.
Well, we have covered incredible ground today. We unpacked the shift to test-time compute, the titans shaping the space, and the tension between opaque power and open-source transparency.
We explored the math of the internal monologue, the tree of thoughts, and how Plan MCTS decouples planning from action.
We confronted grounded self-correction, proving an AI needs external friction like a compiler to fix its mistakes, and we grounded it all in the economics of memory curation and routers.
It's a lot to take in, but it's the future.
It is. But before we wrap up, I want to leave everyone with a final, highly provocative concept for late 2026. Chain of action thought, or COAT.
COAT is the absolute frontier.
We're moving away from models that just suggest solutions in a chat box. COAT models are designed to seamlessly interleave deep reasoning and external action autonomously.
Across totally different software environments, for days at a time.
Exactly. When the AI is autonomously navigating databases, writing code, and running your business without you hitting enter, how do we monitor a train of thought moving that fast?
How do we keep our hands on the steering wheel?
It is a profound question to mull over as we move from reasoning to pure autonomous execution.
A slightly terrifying but exciting question.
Definitely. To our amazing audience, thank you for diving deep with us today. If you found value in this exploration, please support the show. Take a second to like this episode, leave a comment below sharing your thoughts on autonomous reasoning, and subscribe so you don't miss our future deep dives.
We'll see you next time.
Keep questioning, keep learning, and as always, stay brilliant.